Okay, well, good morning, everybody. My name is Brian Salerno. I'm the director of the Bureau of Safety and Environmental Enforcement, BSEE for short. Thank you for coming today. We're delighted that you're able to join us. Before we get started, I do want to just make a quick safety announcement, which is actually fairly obvious. You know, if there's an emergency, there are two marked exits. They're right here. It's pretty easy to find. We're not anticipating any alarms or tests, so if we do hear a bell go off, we'll assume it's real and evacuate. For those who have not yet searched out the facilities, they are through the back door and to the left and right. So I think we've got all the essentials covered with that. I want to welcome you all for coming today. And I especially thank our two distinguished guests for being here. The Department of Interior Assistant Secretary for Land and Minerals Management, Janice Snyder, and the President of the National Academy of Sciences, Marcia McNutt. And we'll be hearing from each of these speakers in just a few moments. I also want to thank the members of our newly formed BOLT Action Team, the Interagency BOLT Action Team, or IBAT for short. It's a group of federal partners from a dozen different federal agencies who are subject matter experts in the areas that are relevant to the problem at hand. We created the IBAT earlier this month so that we can bring together a group of federal experts who can focus like a laser on the problem of connector bolt failure. So I thank them for their stepping forward and helping on this issue. Now, although BSEE is spearheading this effort, we really want to emphasize this is a joint project. We are all receiving information, advice, and counsel from a number of quarters, including very helpful experts from within the industry. As many of you know, BSEE has been looking into the issues related to bolt connector failures for a couple of years now. There's been a series of incidents and what we might term near misses that raise the concerns about connector bolt problems. And we've come to understand that this is very possibly a global problem as well. We are aware of failures, now we're aware of them, dating back as far as 2003. And just for the purposes of illustration, I'll just mention two of those instances because I think it serves to underscore the kinds of risks that we're concerned about. In 2010, a blowout preventer was being tested aboard a semi-submersible drilling rig, Ocean Confidence. She was operating in the Gulf of Mexico. As the test approached 14,000 psi, all 20 of the connector bolts failed. These are 16-inch bolts, 3-inch diameter, and of those 20, about 9 of them they had the studs stripped, and 11 were fractured, so they were all affected in one way or another. Now, this was a shipboard test, so there were no consequences to people and the environment. The consequences were really limited to the lost time and materials suffered by the company. But it's still a pretty serious failure of a critical piece of safety equipment. A second incident in 2012 took place during an actual drilling operation from the drill ship Discoverer India. In this case, the lower marine riser package became separated from the blowout preventer stack, and this resulted in a spill of 400 barrels of synthetic-based drilling fluids. Again, this was traced back to a connector bolt failure. Now, these are just two examples, but they highlight the broader concern. Now, to its credit, the manufacturer of the equipment involved in the Discover India event proactively issued a recall of the suspect bolts. And ultimately, over 10,000 bolts worldwide were replaced. The problem, however, is not limited to that one manufacturer. We're aware of other bolt failures involving other manufacturers. Overall, we're aware of roughly close to a dozen cases where bolts have failed. But no one really knows the full extent of the problem because until recently there was no required reporting unless an incident resulted in pollution or harm to an individual. Now, fortunately, today as of today, we've had no major catastrophes resulting from bolt failures. However, given the nature of the failures that we have learned about, we believe it may only be a matter of time before our luck runs out. And therefore, we feel a great sense of urgency to get ahead of the problem and figure out what's going on before something does happen. Now, Doug Morris, in his session, I think will really delve into some of the findings that we've had on the cases where we have investigated. But it's clear to all of us that we need a much deeper dive to understand what the root causes are for this problem. We really need to leave no stone unturned, and we believe that the bolt problem needs to be solved sooner rather than later. Now, we in the Bureau of Safety and Environmental Enforcement are responsible for offshore safety, and that includes protection of the environment on the Outer Continental Shelf. That's part of our charge. That's why we exist. And the public expects a pretty high degree of vigilance on the part of its regulator. That's very clear in the interactions that we have with the public and their elected representatives. They also, the public, expects a pretty high degree of care on the part of the industry who operates on publicly owned lands, including the Outer Continental Shelf. The bottom line is we all lose if there's a catastrophic incident, and bolt failures could become the initiating cause of such an incident if we don't tackle it now. Now, I think it's important to take account of the fact that this problem may even be broader than just the subsea environment. It's entirely possible that the kinds of issues that we've been seeing may also be present in other industries and in other locations. The kinds of issues we're seeing, inadequate oversight of subcontractors, inadequate sharing of safety data are not by their nature limited to a subsea environment. And that's one of the reasons we established the IBAT, the Bolt Action Team, because our federal partners will be able to bring forth additional perspectives that are likely to help us collectively understand the full extent of the issue. Now, I can't overstate our appreciation for the help we will receive from our federal partners, but I'm also very appreciative for the assistance that we hope to receive from the National Academy of Sciences. This is a subject that's still in the hands of contracting officers, so they tell me I can't say anything about it yet, but we're hopeful that they'll resolve that and that we will actually have national academies engaged as well. These will be two separate but parallel tracks that should lead us to the solutions that we very much need. So today's forum is an important step forward in our effort to find a definitive solution to the problem. So again, I want to thank you in advance for your interest in the issue. We'll be covering a lot of territory today, but before we get more deeply into the technical issues, I want to turn the podium over to the Department of the Interior's Assistant Secretary for Land and Minerals Management, Janice Schneider. And just by way of introduction, Assistant Secretary Schneider oversees a number of bureaus within the Interior Department, including mine, BSEE. She began her career as a fisheries biologist and an environmental consultant, and then went on to obtain a law degree from the Lewis and Clark Northwestern School of Law, where she specialized in environmental and natural resources law. Prior to her present appointment, she held positions with the Solicitor's Office at the Department of the Interior. She served in the Department of Justice within the Environment and Natural Resources Division, and she's also worked in private practice as a partner in the law firm of Latham & Watkins, where she was the global co-chair of the firm's energy and infrastructure, project siting, and defense practice. So in short, Janice has been around energy and natural resource issues for a number of years, and I know from my interaction with her that she's intensely interested in helping us meet the challenge of failing connector bolts. So please join me in welcoming Assistant Secretary Janice Schneider.
Thank you, Brian. Okay. I wear glasses, but they're not going to help. So I'm going to hold this up here if that's okay. Thanks very much to everyone for being here this morning, and good morning to all of you and for folks who are watching at home. I wanted to join today because I think we all realize what a very serious problem we have on our hands. As Brian mentioned, I have worked with the energy industry for, I'll say, many, many years, or even many decades, as the case may be. And really, as we all know, the importance of functioning, reliable equipment, components and parts really cannot be understated. I know that it can be challenging to convince others of this fact and their significance. I mean, for most people, bolts are really about as generic as it gets. And a lot of people just assume, well, you know, of course they're going to work. However, the two examples that Director Salerno just cited demonstrate that not only how critical bolts are, but also that the failure of such a simple component has the potential to lead to a major problem. And as the offshore oil and gas industry continues to move into deeper waters and more challenging undersea conditions, it seems to me that our challenge becomes even greater. You know, I read an article recently in the Wall Street Journal quoting a CEO of a major offshore drilling company who told investors in June that the company had count them, four unplanned stack pulls in the second quarter, 3 of which involved failed bolts. That's just one company, and that's in just 3 months. So this is very serious business. So I'm here today to communicate a very simple message to everyone in this room. We need you, we need your help, and we need your support. As Director Salerno said, together we will figure this out. It will take determination to solve the problem and the resources to make it happen. Both will be brought to bear in this effort. The Department of the Interior is putting extensive resources into this effort. But due to the seriousness of this issue, we want to make sure that all of the top thinkers in this area are engaged in helping us solve this problem. As Director Salerno just mentioned, we suspect that the issues that BSEE is seeing may go well beyond the industries that BSEE regulates, and this may potentially impact other safety-related equipment. So this work that we're asking you to all participate in has broad-ranging applicability. And for these reasons, I shared Director Salerno's appreciation for those federal experts, both within the Interior Department and outside the Interior Department, who have stepped up as part of the Bolt Action Team. And I also look forward to working with the National Academy of Sciences to conduct, hopefully once we get this contracting stuff worked out, a thorough study of the problem. Many of today's participants are experts on this topic. Some of you are here because you're trying to understand the problem, and some, like me, are here to offer support for BSEE and the other entities that are involved. Some of you are probably part of a work group set up by the American Petroleum Institute, a parallel effort that is addressing the issue of bolt failures, and some of you represent affected industries. Be assured that the Department of the Interior is 100% behind everyone's efforts to solve this problem and to solve it soon. Between our collective action, whether it's prior BSEE internal investigations, the Bolt Action Team, the National Academy study, forums like these, and industry leadership, we will have the ability to better understand the breadth and the depth of the bolt problem. So I commend your Bureau, Director Salerno, and our many partners for having the foresight to act proactively. This is exactly how an organization operates when it lives its mission. The American people expect us to operate with safety as our first priority, and your efforts to solve the bolt problem before it makes headlines demonstrates that BSEE is really living up to that expectation. I know that across the vast expanses of the outer continental shelf, with all of the various facilities, a lot goes right on every given day. In the 5 years since BSEE was created, we have seen that there are bends in that arc towards a safer OCS. There are a lot of hard workers out there doing their jobs well, and a lot of companies that are committed to fostering a culture of safety. But I think we all know that it only takes that one combination of circumstances to put all of our safety systems to the critical test. With so much riding on our critical safety equipment, we have to make sure that all components, including bolts, work as designed. Everyone is counting on you and us to make sure that that's the case. This is a problem that's going to be solved because we have the best minds working on it, including all of those of you who are sitting here today. All of us know from experience that prevention is vastly better than responding to incidents. So while some may worry that the cost of fixing the problem may be too great, we really need to set that aside. We need to be driven, as the director said, by the public expectation that we're assembled to prevent the possibility of a catastrophic failure. Anything less than our best efforts to solve this problem are simply unacceptable. In a few years from now, I'm hoping we can all look back and feel good about the fact that we're part of a solution that prevented a problem from actually fully manifesting. You know, prevention never makes headlines, but there is no nobler calling than the call to save lives and to protect the environment. And that's exactly what's happening here today, and that's the journey upon which we've all embarked. I want to close by thanking all of you for coming today, for your willingness to help, to listen, and to learn, and to support this effort to find solutions to this very critical issue. Thank you.
Well, thank you very much, Janice. And let me just say, we truly appreciate your support and your encouragement as we collectively seek to tackle this issue. And we will certainly seek your advice as we proceed in this process as well. Our next speaker is Dr. Marcia McNutt, who I'm quite sure is well known to many of you. She has a long and very impressive list of credentials. She earned her PhD from Scripps Institution of Oceanography. She was the winner of the 2007 Maurice Ewing Medal for her contributions to deep sea exploration. And of course, she was a professor at the Massachusetts Institute of Technology, and that's just for openers. Since 2009, when she came into the Department of the Interior, I think initially as an advisor, a science advisor to the secretary, and then subsequently appointed as the 15th director of the U.S. Geological Survey. You know, when she was appointed, it's a Senate-confirmed position, and she received unanimous support from the Senate, which I think is quite impressive. That's not an easy thing to do. When the Deepwater Horizon tragedy occurred in 2010, she was thrust into a leadership role in helping to solve those problems. And in particular, she led the flow rate technical group, working directly under the National Incident Commander. And I'm sure many of you can remember the daily media footage on CNN every night and many other news outlets looking at the rate of discharge. Remember that video of the flow? No one could figure out exactly how much was coming out. And that was critically important from an operational response perspective, but also from a legal perspective. Well, Dr. McNutt figured that out with her team. In 2013, she became the editor-in-chief of the prestigious Science magazine, where she's been credited with setting up that publication for success in the modern publishing environment. And then in 2015, she was named as the next president of the National Academy of Sciences, and a position she assumed during the course of this summer. By the way, those last couple of items, she was the first woman. She was the first woman to lead the USGS, the first woman to become editor-in-chief of Science, the first woman to become president of the National Academy of Sciences. So I guess, you know, I don't know where to stop with your list of credentials, but I'll stop there. It's a very long and very inspiring list. So please join me in welcoming Dr. McNutt. Thank you.
Okay, it's just embedded in there, so it should play. Well, good morning, everyone, and thank you very much for inviting me to come speak at this very important forum. So I decided to take a sort of larger view rather than talk about the bolt problem in general, talk about this general issue of problems when failure is not an option. And in thinking about this, I remembered distinctly a presentation I heard from a former colleague of mine, Nancy Levison, from MIT, who's an expert in industrial safety. And she and I were on a panel after Deepwater Horizon, and she reported on a conversation she had heard from some people who thought that in the wake of Deepwater Horizon, that while as tragic as that oil spill was, they felt that oil spills were going to be very difficult to stop simply because drilling in deep water with these complex wellheads had simply become so complicated that it would be very difficult to make them absolutely foolproof. And Nancy's response to that was that there are many engineered structures that are very complicated, and yet we have made them virtually fail-safe. And one example she gave was the fact that nearly 2 million people in the US alone put themselves into aluminum cans that go up to about 40,000 feet every day in the air and come back to the ground safely after traveling perhaps thousands of miles. And they do that largely without incident. And that is a very complicated process. And if they couldn't do that safely, the airline industry basically would not be a profitable enterprise. And she used that as but one example of an industry that has had to look at all modes of failure and track them to the ground in order to be profitable. Now, it's not as though accidents don't happen, but they are rare. This is one of the few that certainly, I mean, we do have terrorism, but there aren't that many that cause major losses of life due to actual failure of the aircraft itself. This was one of a Concorde that happened in July 2000 that was taking off on a runway at Charles de Gaulle. And this was an interesting one because it brings up a point that Assistant Secretary Schneider said, from the standpoint that I believe everyone on this plane died in this one. It was this small piece of debris on the runway that caused a tire to blow on the Concorde, and the debris from the blown tire came back and hit the wing and hit the engine, and the Concorde crashed. And as you all know, the Concorde is no longer flying. Of course, there were reasons other than just this crash, but it was the beginning of the end for the Concorde. So, you know, it's sometimes little things that can cause problems. Another example of the simple things that can cause disasters, Assistant Secretary said that a bolt is a simple thing. Another example of a very simple thing is an O-ring. And everyone recalls the Challenger disaster that began with a very simple thing that was an O-ring. And these O-rings on the Morton Thiokol solid rocket boosters were tested on certain conditions, but here was a very unusual condition where they had freezing temperatures in Cape Canaveral, Florida. And so here was a situation where these were operating out of their normal operating conditions, and they had not been thoroughly tested outside of these normal operating conditions. So again, it was a failure in testing. Another example was the Columbia disaster, where the space shuttle disintegrated over Texas and Louisiana, and the problem was traced back to the launch, where a piece of foam insulation broke off the external tank, struck the left wing of the orbiter, and at that point, it caused damage to its thermal shielding, which could not have been repaired in flight and caused problems on reentry. Now, let's turn to the ocean and compare what some of these problems are to the ocean, because I want to make the point that I think some of the problems that we have to face in actual tracking down failure modes in the ocean can actually be more difficult than just making something like the Challenger or the space shuttle flight safe. So let's look at ocean versus space in terms of power and the problems we have to face. If you want to power a spacecraft, all you have to do is put solar panels on them, unfurl them, and you've got power in space. If you're working under the sea and you want to power something, you've got a very, very difficult problem, because you cannot just use solar panels, because solar energy does not propagate underwater. So instead, you either have to use batteries, you have to use cables, or some other way. Submarines use nuclear reactors. Getting power into the deep sea is a much more difficult undertaking, and many of the failures we have in the deep sea have to do with power failures, either lithium battery failures or failures of power systems, batteries running out. And this is something that we don't have in space to the same degree that we have under the ocean. So the advantage is definitely in space in terms of trying to deal with power systems. If we look at communications, again, the advantage is in space. Electromagnetic signals travel easily to space. We could talk to the Pluto mission easily all the way out at the furthest edge of our solar system, whereas it is very difficult to communicate to anything underwater because, again, electromagnetic signals do not communicate underwater. We have to use cables. We have to use sonar, which has much lower bandwidth. And so the advantage is to space in trying to communicate. Again, we can have communication failures when cables break. We have multipathing effects. We have all sorts of difficulties in communicating underwater. And again, a lot of failures happen. Or sometimes we have problems determining what actually was the failure mode because of problems in communication. So that's why there are difficulties underwater compared to space. Fouling. You can put something out in space, and it can be out there for decades, surveying Jupiter, going out to Neptune, and if you look at it decades later, it will look no different than the day it was launched. You put something down in the ocean and pull it back, The one in the lower left-hand corner was out in Monterey Bay for a matter of a month, and it comes back looking like that. The one on the right, it went down as the seismometer in the upper right-hand corner and came back as a massive sulfide deposit a couple weeks later. So there's biofouling and there's geofouling that happens in the ocean, which makes it very, very difficult. There's corrosion that happens in the ocean, there's deposition, and there's biofouling. So all of those make it much easier to put something in space and expect to get it back looking like it did. That never happens in the ocean. There's corrosion, there's deposition, and there's biofouling. So again, the advantage is space in terms of anything that happens chemically, biologically, and physically. Now, the one place where oceans have the advantage is in the launch. Every time I've gone out to sea and thrown something over the side of the ship, we've had a successful launch. It has indeed gone to the bottom of the ocean successfully. And in fact, if you go back to the problem with the Challenger and Columbia, both of those problems can be traced to problems at launch, the O-ring failure and the foam insulation failure. Both of those were actually problems at launch. And so the ease of launch translates into practically no penalty for weight in the oceans as compared to space. And so the one thing we can say is that oceans do have an advantage on the launch, and that's about the only advantage that they do have. Okay, so does that mean, therefore, that all of these translate into much more difficult, should we throw our hands up in the air and say that we can't solve these problems in the ocean? Or was Nancy Leveson right that there is a systematic way we can go and solve these problems in the ocean? Well, one point that Nancy made was she brought up this man, Admiral Rickover. Admiral Rickover was basically the father of the Navy's nuclear fleet. And for 30 years, he oversaw the development and the advancement of the US Navy's nuclear submarine fleet. And in particular, I even recall in 1963 when the Navy's quietest and fastest submarine, the Thresher, was lost with 129 hands aboard in 1963 during actually one of its testing cruises. And there are still, theories as to why it was lost, again, because of problems with communication. But Rickover was extremely upset about the loss of the Thresher. And he implemented a rigorous submarine safety program, which he called SubSafe. And what's interesting about that is before SubSafe, the Navy lost 15 submarines in non-combat incidents. Since SubSafe, only one submarine has been lost, and that one submarine was not SubSafe certified. So that is a pretty incredible record. 15 prior to that, zero SubSafe certified subs since that, and only one that was non-SubSafe certified. So I think my question to all of you, therefore, going forward is, who is going to be the Admiral Rickover for your bolt problem? Who is going to step forward and say, I'm going to come up with a program that is going to make deep sea installations safe, and come up with a testing and certification program that's going to solve this problem, such that prior to this, we've got this record of failures, and afterwards, any installation that goes through this certification program, 0 failures. And I think that's a worthy goal. Now, I should say that after, is there another slide? I guess it's missing. Well, the National Academy did do a post-Challenger evaluation that was asked for by President Reagan. And the National Academy recommended that, that there would be a full systems approach to the continuous identification of safety risks, not just failure modes and hazards, and quantitative objective evaluation of safety risks. And all of this was very much in keeping with Admiral Rickover's approach to addressing the safety problems in the nuclear fleet. So I'll end there and wish you all much success in your task ahead. Thanks very much.
Oh, thank you, Dr. McNutt. We really appreciate you taking the time to share your thoughts with us, and really an inspirational message. I've always been quite intrigued by the SubSafe program myself, and I think that's a very useful challenge to us today. At this point, I believe Doug Morris is going to introduce the first panel, or at least give the where we're going with the first panel. So, Doug, would you like to provide that?
Would you guys come on up? Thanks, Brian. I have with me today Joe Levine, who is the head of our Emerging Technologies branch, Troy Trosclair, who's a Deputy Regional Supervisor, Gulf of Mexico Field Operations, and Dr. Candy Hudson, who's the Chief of the Systems Reliability Section. Our goal in this first session is to describe what we know and what we don't know concerning this issue. During the second session, we will discuss the path going forward. However, I would first like to, hang on 2 seconds. Got it? However, I'd first like to tee up the issue by giving a description of our Bureau and our offshore operations. Here's our mission statement, which is to promote safety and protect the environment while ensuring the diligent development of offshore resources. We have broad jurisdiction over federal offshore lands. We have more than 800 people located in Washington, D.C., Louisiana, Texas, California, and Alaska. There are currently more than 2,300 facilities that bring oil and gas to the surface and transmit it to the shore. These facilities produce almost 20% of our domestic crude oil production. They range from relatively simple structures located in shallow water to billion-dollar deep water projects. And we are required by statute to inspect each of these facilities at least once a year. We are also responsible for providing oversight over the drilling rigs that move onto a lease and drill the wells that produce the hydrocarbons. At the end of July, despite low oil and gas prices, we had more than 55 rigs operating in the Gulf of Mexico. There are 4 general types of drilling rigs that operate on the OCS. They're demonstrated here. For the purpose of today's discussion, we are focused on deep water drilling rigs that use subsea blowout prevention equipment. So that's the semi-submersibles and the drill ships. Here's a picture of a floating drilling rig. The blowout preventer is located on the seafloor. This equipment is used to confine well fluids to the wellbore. That's a definition of API Standard 53. And in an emergency, to shut in the well and prevent a blowout. So when it's needed, this equipment simply has to work. And here's a picture of a BOP stack. I'm not going to describe how it works, except to state that this is a huge piece of complex equipment containing multiple components that must work in very challenging environments. Various types of bolts, studs, and fasteners are used to assemble and connect all these components. As we will be discussing in a moment, there appears to be issues with the various fasteners used in this equipment. As noted before, that the fact that we are experiencing problems with what was assumed to be the simplest component in a complex system is troubling to BSEE and the reason for this forum. 2 other items for consideration before we get started. First, this equipment and these drilling rigs are moved from lease to lease and often moved to other areas of the world. As a result, this issue has potential international impacts. Second, when addressing issues related to this equipment, we have 3 parties involved. We have the original equipment manufacturer, the drilling contractor who owns the BOPs and performs maintenance and repair, and third, the operator who hires the drilling contractor to drill a specific well. Each of these parties has legal and commercial considerations that complicates the resolution of this issue. Okay, so let's get started. I'm going to turn this over to Joe Levine. Joe.
Thank you, Doug. Good morning, everybody. We have a pretty intimate crowd, which is good. That means we have managed to get just the specialists and the people that really have a vested interest in connector reliability. So I think that's a real positive step. I'd like to echo everything that Janet and Brian, Marcia, and Doug already mentioned in regards to connectors and their use on the Outer Continental Shelf. Okay. Basically, this session will look at 2 things, actually 3. First, I'll give you a brief overview of the technical evaluation process, the one that we have put into place, which led to the published evaluations on connectors. Then Troy Trusclair from our New Orleans office will get up here and discuss 4 or 5 of the connector failures that we've experienced, both the ones that we have our reports out on and several others that we're currently investigating. Then Dr. Hudson will follow up and provide us more of the details in regards to the various areas of concern the agency has become aware of in regards to connector manufacturing, materials, and operational procedures. So that's how this session will go. I think it's probably best if we just kind of keep any Q&As to the end of the session. At that time, we'd be more than happy to address anything that we can with you. Okay, as Doug mentioned, his office, the Office of Offshore Regulatory Programs, this is the office where we conduct our technical evaluations out of. Basically, this first bullet is my vision, my view on what we're trying to do with these evaluations. We're evaluating a piece of manufactured equipment, a failed piece of manufactured equipment, trying to determine whether it was fit for service or not. What I mean by that is, as you all know, there's a series of manufacturing specifications, recommended practices that are put into place that an OEM abides by when manufacturing the widget. Here we're talking about a fastener. Then there's also a series of operational or environmental parameters that the widget needs to function within during its life. This could be the external hydrostatic pressure, 10,000 feet of water, 4,400 PSIG, bottom hole pressure inside the equipment, 10,000 PSI, bottom hole temperature, 300 Fahrenheit, external temperature, 31 degrees, corrosive, sour conditions inside of it, sediment, high flow rate. So these are the operational conditions. So we look at the piece of manufactured equipment during our evaluation, and we make an assessment through our work if this piece of equipment truly was designed, manufactured, and used within its fitness for service envelope. As we go through the report, one of the 2 goals that we are trying to accomplish is to identify gaps, any gaps in BSEE regulations, perhaps, that are governing this piece of manufactured equipment, or any gaps in the industry standards that are either incorporated by reference in the regulations or not incorporated by reference. As an example, you know, we have subsurface safety valves 14A, it's in the regs. 20E has come up in fastener discussions. It's not in our regulations now. So we look to see if there's gaps in the regs, standards, or any other kinds of processes that we've identified as a possible contributing cause to the failure, and the goal will be, as we move forward, to try and address and close these gaps. I think it's really important to look at the differences here between these technical evaluations and the more traditional MMS, BOMER, BSEE, regional panel investigations, and District 2010 investigations. They're 2 different animals. Those of you that have been in this business a long time know the 2010s and the panels. We conduct these investigations when there's been an accident or an incident in accordance with our 30 CFR Subpart A requirements. We state out when an operator needs to tell us about an accident, injury, a fire, a loss of well control, etc. We conduct these investigations. They're fact-finding, yes, but there's also an enforcement component to these 2010 and panel investigations. We're looking to see compliance with 30 CFR regulations, incorporated standards, and perhaps what I call conditions of approval that have been attached to an application for permit to drill or an approved plan. We're looking for violations there. If we find a violation, we conduct an enforcement activity, such as issuing an INC, incident of noncompliance, or a civil penalty, which is currently $40,000 a day per incident. So there's an enforcement component to these traditional 2010 and panel investigations. The technical evaluations that we do, the two on the failed connectors, we have no enforcement associated with it. They're 100% evaluate, find out facts, share the information, with the goal being to raise the bar of safety, raise the bar of environmental protection on the OCS and perhaps globally. So big difference in these two kinds of investigations. Looking further at our technical evaluations, I look at it also as BSEE is independently validating how the OEM, the manufacturer, has used the RPs and specs in regards to quality assurance, quality control, in designing and manufacturing the widget, such as a connector. We're also independently validating its ability to perform within the fitness for service requirements I've already mentioned, and how reliable and dependable the device is. So that's another one of our guiding principles as we conduct our technical evaluations. The second bullet, industry collaboration, is critical. We made the initial assessment on this a few years ago when we first started on our technical evaluations. If the goal, like I said, is improve safety, protect the environment, look at some causes, share the information with industry to prevent similar occurrences happening in the future, we felt the best way to do this was not to have the agency conduct these evaluations in a vacuum, but to actively collaborate with our partners. And any of the companies in this room that have been involved in any of the three technical evaluations we've conducted know that we mean what we say here. We conduct a draft report, and we send that draft technical evaluation report to the OCS operator, drilling contractor, and OEM separately, and ask for their input and their concerns. And then we actually go down and meet with them face-to-face over a series of meetings and discuss the points. And that way we feel we end up with the best product because we have listened and we've tried to address everybody's concerns. I'm not saying we always take every comment, you know, like our rulemaking. We don't. But we definitely listen. And as some of you know, we discuss all your points. So we decided collaboration was key to making this a successful program. You'll also see in our reports a series of recommendations. These recommendations, after we've conducted our evaluation, go back to either the agency or the industry. We may say to ourselves, this situation here reeks of policy and procedural deficiencies that we need to change, or new regulations that we have to implement, or NTL, notice to lessees, that we should set out. We also have recommendations back to industry. modify existing standards or develop new standards. And here in connectors, I know API has an active work plan. On this point here, we had some recommendations, which Candy will go into in more detail. But we had some recommendations on inconsistencies amongst the various API, ASTM, ASME standards in regards to material properties which govern manufacturing of connectors. So API has formed a work group, sent us a work plan, a pretty robust work plan. I think Trent over here is spearheading that project to try and look at this, try and harmonize some of the information in these standards better. We also have recommendations on safety alerts. After we released our first evaluation, we also followed up with a safety alert. I think it's a real good way to share the information and our concerns with industry. And finally, another recommendation could be a research project. We may believe we really don't know enough to manage the issue in the best way possible, and perhaps research is a good solution. It could be a BSEE sole source kind of research project, or my favorite, the JIP. You get a broad cross-section of companies in a JIP, so I think you get a better product out of the research. So we have a whole host of opportunities here to address the concern via these recommendations. Before I pass this off to my colleagues, I had a couple of observations. I think others before me today kind of hinted at this, but before 2 or 3 years ago, when we started our technical evaluations, if I ever thought about a connector at all, when I looked at a subsea BOP, a 200-ton BOP, $500 million BOP, if I ever thought about a connector at all, I thought it was an inconsequential, insignificant piece of hardware. But I'll be honest, I never thought about a connector at all. I looked at this subsea stack or an LMRP riser system as, you know, was it designed in accordance with appropriate documents? Is a company following the 30 CFR regs, et cetera? Now, today, I certainly don't see a connector as inconsequential or insignificant. I see it as a critical piece of hardware, which is really the Achilles heel of this critical piece of equipment. If it's not functioning right, if it's not manufactured correctly, all it takes is a couple of those, and we could have another Macondo or something similar from this piece of equipment. So I look at it totally different today. And also, now that we've had a couple of years to kind of look through some of the information on connectors, kind of surprised me. In the years 2001, 2, 3, et cetera, you know, when you look through the reports, we've seen these failures before. It's not a brand new occurrence. I think the difference is back in 2003 when we started getting this info trickling in willy-nilly, BSEE and, well, MMS at the time and industry really just looked at it as, oh, a bolt failed. Okay, let's correct it and continue operations. Let's correct it, continue permitting evaluation. So that mindset has totally changed today. I don't think anybody in this room looks at it as a bolt failed, replace it, move on. I mean, now we're trying to really understand why it failed. So those are some of the observations I've picked up over the last year or so that I've been conducting this work on connectors. So I will end, and I will pass this on to Troy Trusclair. I'm sure Most of you know Troy. He's out of our New Orleans regional office, deputy regional supervisor. Troy and I have actually worked together on and off for 25 years, so I know him fairly well, and I'm sure he's got some good input to provide the group. There you go, Troy.
Make sure I can understand. Look, I'm gonna first apologize. I'm from Southern Louisiana, so my accent, some people say I have an accent. I don't think I do, and this thing might not be tall enough. But excuse me, I hope I don't need any kind of interpreter. But thank you, Joe, and I tell you what, I do like the outcome here. It looks like a lot of people are interested in this issue, and it's something we definitely need to get a grasp on. Make sure I can follow these. Okay, as you can see, this is a summary, and BSEE has been, I guess, looking at these incidents that have occurred for the past several years, and there's been several fastener failures on these critical pieces of equipment for well control, specifically the BOP stack. And it did not affect just one BOP manufacturer. In fact, it affected all three of the major manufacturers for BOPs. I'm gonna try and go through these things fairly briefly, these incidents, but this is kind of a summary of these. The first one, the director did mention this one a little bit, and I'm gonna go into a little bit more detail of this event. This was an LMRP failure, and real quick, let me see where the pointer is on this thing. Oh, that was not it. Is there a pointer on here? What's what? Ah, all right, so right here is an LMRP connector here. And as you can see on the bottom of this, there's actually what they call a wellhead connector. So this event with this LMRP connector that separated, which had all 36 bolts fail, and of course there was a release of 432 barrels of synthetic base fluid. This event was not only affected LMRP connectors, but it also affected several rigs that actually had that same connector as the wellhead connector. And as you can see, the BOP stack itself is right here. So if that would have failed, we would have really had a serious problem here. You would not have had the BOP stack in place. So the OEM at the time actually recalled approximately 11,000 of these fasteners. One other thing I want to make a point of is, here is the actual connector itself with all the failed bolts. But this actually had a pollution event associated with it, so BSEE was contacted because 30 CFR 250-188 requires you to report incidents of pollution. So this was reported to us. We immediately initiated an investigation. Part of that investigation was to ask the company to come in with a preliminary root cause analysis of these bolt failures. And about a month after the incident had occurred, they did come in and brief BSEE on the incident and what was the outcome. From there, BSEE actually contacted the OEM and their equipment manufacturer and tried to get what scope are we talking about as far as Gulf of Mexico rigs, and it's how involved it is, what kind of impact it's going to have on the Gulf of Mexico operations. They listed 25 rigs was associated with this. So one of the things that BSEE started doing was calling the operators of those contracted rigs and trying to find out, hey, were you aware of this bolt incident? And the manufacturer did go out with a bulletin. And what is your plan forward as far as your well operations? And what wound up happening was BSEE did order the companies to go ahead and T&A the wells at their safe stopping point, pull the stacks, and replace them with other bolts that actually had, I think Dr. Candy Hudson's going to get more into the metallurgy and some of the findings of the bolt issues. But what this one was is I think it was a post-heat treatment of some of the coatings. So all these rigs had to replace those bolts with the newer bolts. And one of the things that BSEE also required was we wanted a certificate of compliance that the coatings had been post-baked accordingly. We had one of the third-party certification of that. And we also wanted a third-party certification that the BOP was now fit for service. So But one of the main things to look at is, like I said before, this part right here. If there was a failure and it was a wellhead connector, it could have been a bigger difference. In fact, this well here, they were actually, I think, 1,500 feet below the 18-inch shoe. So it was a benign hole section that they were in. But it could have easily been a well operation where you actually had exposed hydrocarbons. And if you had exposed hydrocarbons and you had a failure on this, you actually would not have had any protection whatsoever. So. Next event, June 2014, we had a failure. Now this one was the actual BOP stack was actually on the deck on the stump, and they were just doing some maintenance in between well maintenance. And what they found on that connector was there was 9 out of the 20 fasteners had failed. This also was an LMRP connector. This was considered a near miss event. This one here, on October 2015, the blind shear ram actuator fasteners had failed. A lot of folks call this the booster cylinder, but this is what takes the hydraulic energy to actually ensure that the blind shear ram will cut pipe that's inside of this inside the BOP stack. And this failure here, 6 of the 8 fasteners had failed on the upper ram. BSEE's currently still evaluating this failure. But some of the others, this is a photograph of the fasteners that had failed in this situation here. And this is how they found it, and you can see some of the bolts are on the outside. We had some other known failures. These happen to be the blade connector. So here's your ram block, here's your actual blade, your cutting blade, and here are the fasteners that actually attach the blade to the block. And in these cases here, these bolts had failed. Now that's what holds the blade in place to be able to cut the pipe, the drill pipe. So we've had several of these incidents, but fortunately, these incidents occurred while they was on deck doing stump testing. It didn't happen while anything was in service. But this could be same kind of thing. If this would have happened while you were in an actual hole section that had an open reservoir to it, we could have a problem. It'd be unprotected. So from here, we'd say there was some subsequent failures. And the equipment manufacturer went out with a safety notice, and the fix was to go ahead and reissue new bolts. That was a 3/16 inch thicker flange, and I know I'm probably talking sideways, but anyway, that was the fix on that. One of the things, as BSEE starts looking into these bolt issues, we found out there was a lot of other bolt issues that we really didn't know about. And it makes sense, though, because the only time we're going to find out something is if it's a reportable incident. If there's a pollution incident or some other accident that's reportable based on that 188 regulation. So from that, we found out there was several other fasteners that had failed. And I think the director spoke about some of these. But that's one of the things I wanted to talk about. Those blade incidents, the way we found out about it was the equipment manufacturer actually sent out a bulletin to the rig contractors. And the rig contractors, of course, got with the operators, and some operators actually said, hey, I think BSEE might need to know about these issues. But there was a gap of time there. So some of these bolt failures we didn't find out about till about a month and a half after some incident actually occurred. Hopefully with the new requirement, the new well control rule actually, I think it's 257.30 Charlie, requires now these failures to be reported to BSEE, to OORP, to Doug's group. And hopefully we'll be able to get a little bit, reduce that gap of time, so we can be a little bit more proactive as an agency on this and get involved. One of the other things I wanted to talk about is the impacts. This is just So for the first one, the LMRP connector, we had 25 rigs that was affected. Not only was it 25 rigs affected, but after the Deepwater Horizon incident, we were required to have a containment. Every deepwater operation had to have a containment demonstration or a containment plan. One of those connectors were associated with the MWCC, one of the containment groups, stack also. So at that time, we needed to get that changed out because that's one of the rationale why you're able to go ahead and drill, because you do have this containment equipment on the beach that's ready to be deployed. And the average downtime, and this was not a whole lot of science, but I just took the days, because what we did was just track the days from the time the stack had to be pulled to the time the stack was ready to be deployed back in the water, and just divided the number. And it was an average of 17 days at that stack just for this replacement of these bolts. LMRP connector failure in June 14th, only one stack, and that stack was actually on the rig, so there was 0 days there. The BOP actuator failure, 2 rigs were involved, pulled the stacks and replaced those fasteners, average of 18 days downtime on that. The upper blade fasteners, both the failures, this was in March 2013, 2 rigs. One rig, the stack was actually on deck conducting maintenance, and the other stack had to be pulled and replace those fasteners. That's why you see 7 days. It was actually 14 days for one rig. And this other incident that happened in December 2014, along with May 2016, the one that happened in December 2015 was I think it was a blind shear ram failure. But the most recent one was also associated with blind shear rams, and it required 8 rigs to pull their stacks and replace those fasteners, an average downtime of 12 days. But I believe, is that all I got here? Yeah, that's all I have here. But I just want to echo the sentiments of Assistant Secretary Snyder and Director Salerno, exactly what he stated before, that these incidents, we definitely need to get on top of this, get a hold to it. And this critical piece of equipment, the BOP stack, is that's our safety equipment for drilling operations subsea. And so if we don't get a hold of this, it's quite possible we could have another incident. And as Dr. McNutt stated, failure is not an option, not for industry and not for this agency, and definitely not for this country. So I'll turn it over to Dr. Candy Hudson. She'll probably get into a little bit more of the details of these failures. Appreciate y'all time.
Thank you, Troy. Yes, Dr. Hudson now will give us an update on some of the areas of concern from our evaluations.
Thank you, Mr. Levine. I'm going to tear off Troy. Thank you, Troy. I'm going to speak in more detail than the weeds about the material-based failures. I'd like to give a disclaimer also about my accent. I tend to pick up the accents of others. I've been... No. I spent time in the Deep South as well. I spent time in the Midwest, East Coast, and have a lot of friends from the UK, so I tend to pick up accents. And I need actually a little help. I can solve a 4th-order nonlinear homogeneous equation, non-homogeneous equation, but I can't seem to operate the prompter. Middle button. Oh, thank you.
Is that what it is?
Yeah, I think so. Okay, so going a little deeper about the first fastener failure, some of the key findings. What BSEE has identified in general is that there is a significant material properties gap. There's a difference in requirements of the material hardness, the ultimate tensile strength, and the yield strength. And what has been recently brought to attention by industry is any hardness values greater than 32 Rockwell scale C is a concern for critical equipment use subsea. What BSEE and the team has also identified is that there are OEM quality control manufacturing process concerns, various concerns in regards to if there is subcontracted vendors, non-compliance to the OEM manufacturing specs, elaborating. Some of the quality management systems only audit to the first tier subcontracted vendors, and some of the processes are subcontracted further down the chain to second, third tier, and further down vendors that may perform processes, such as starting from the original raw batch, or maybe there may be some concerns about the improper material casting, improper heat treatment, and there was also concerns about the latest edition, whether or not that was followed through for ASTM standard 2007. Prior to that, there was the coding standard ASTM B633 1998. This one had required a different type of material property value, which required subsequent heat treatment after the coding processes. After that, the committee met in 2007, and there were different material property values that required a post-bake after coding based on the material strength values. What was identified in this fastener failure, this was the second one, environmentally assisted cracking was identified as the failure mode due to hydrogen embrittlement, and there was a wide variation in the material property values, ranging from 27 to 41 on the Rockwell scale C. The failure mechanism is still not quite fully understood as to where there was actual cracking before the manufacturing processes, the machining, or whether or not this cracking occurred during the actual service. I will attempt to use this prompter again. Eureka. I will speak about this and then I'll go back if everyone would bear with me. So elaborating on some of the other known failures, as Troy spoke earlier, on the upper shear blade to casing ram back fastener failures, some of the key findings that was also of concern is the installation concerns. Were the fasteners consistently applied in the right torque manner? Some of the fasteners were torqued beyond the material strength, the yield strength per the spec. Also, concerns about the appropriate lubricant, and again, the heat treatment concerns of the actual fasteners. Okay, I'm going to try and go back. Okay, it looks like I went for it. So the October 2015 failure. What was identified for this evaluation 3 for the blind shear ram? Again, the failure due to hydrogen-induced embrittlement. High material hardness of the cylinder stud. If you can recall the picture that Troy had showed earlier, what was really concerned is there was a significant high hardness values of 41 to 42 Rockwell Scales 3, and would like to elaborate again that this was a 4140 alloy. Inadequate post-bake were not appropriately followed per the spec, so therefore there's concerns about post-baking after the coating process. Hydrogen may become entrapped in that initial layer and may expand and may contribute to the hydrogen-induced failure. So that's also a concern. Let me try and go back. There we go. Good job. I tend to do by doing, so I'm actually living up to being an engineer, I see. So going about the fastener failure 1, what was identified was significant, again, material properties gaps. There was concerns about the hardness values beyond 32 Rockwell hardness C. Some of the material properties were really, really high as 38. And these bolts were used for subsea service. There were coating concerns. There was an initial coating that was used subsea, and there was concerns as to this coating may actually promote the release of hydrogen and promote environmentally assisted corrosion cracking. Again, expounding the broad range of material property requirements among applicable industry standards. And there was concerns about quality management systems, oversight, and audit and control. The QMS system really only audited down to the first tier, and as such, there was non-compliance to the OEM manufacturing spec by some of the subcontracted vendors. There needs to be a better oversight of this. There was also concerns about the post-bake process was not followed. An older standard was utilized for this one, ASTM 1998. And based on that standard and based on the spec, the material hardness and the material yield strength was not required to do a post-bake. Subsequently, there was a more recent addition, but based on the standard that was followed per the OEM spec, but a post-bake really should have been applied after the coating process. The mode of failure was identified. Again, there tended to be a common theme as a result of these material properties and the coating processes, no post-bake. Environmentally assisted cracking again, and due to hydrogen embrittlement. And again, elaborating, there is a broad range of hardness values going from 34 to 38 Rockwell scale C. But that is also per the spec. Okay, so going to other known findings, the BOP flange failure of June 2010, as Troy touched on. This was the one that BSEE had lately known, and I would like to also expound upon the colleagues that had spoke before me. This is a really, really great concern that there needs to be information and data sharing. Data sharing could help in trying to identify what's the best action plan and what's the best resolution. The alloy here was not 4140. This was actually an Inconel 718. For those of you in the aerospace industry, you may be familiar that this is one of your common alloys that are used. However, this is not known to be used in some of the oil and gas industry. The hardness values was 42 to 47 Rockwell scale C. And as a result, there has been some updates to API industry standard as a result of this. Again, hydrogen stress corrosion cracking, and the concerns with the hydrogen being the byproduct of the cathodic protection, which promote the free release of hydrogen, therefore diffusing into the material substrate, becoming a trap, and causing the corrosion failure, the stress corrosion cracking. So, as Joe mentioned, there is basically 4 areas of concerns that was identified. The first one, design standards. What was identified is there are significant gaps among all the applicable industry standards, inconsistent requirements for material properties. And as a result, there is a need to have harmonization among the requirements. The second one is manufacturing processes and procedures. Concerns with, is there appropriate oversight with the initial raw material processing, the subsequent machining? This is one for further study. Would like to suggest for further research. There may be concerns in regards to whether the threads are cut or rolled that can contribute to some of the fracture or the pre-fracture of these bolts. And of course, when the bolts are fastened and torqued beyond their yield strength, depending on the threads, that can also play a part. Heat treatment. Again, if the material is appropriately heat treated, and as all metallurgists know, you have to follow that TTT diagram, time, temperature, transformation. We'll have to thank our thermal instructors about it. But something simple as just throwing something in the oven, you may think it's completely done and heated, but depending on where it is within that furnace, it may not be appropriately cooked on the inside. I guess the best way I can describe is you put a cake in the oven, you take it out, it looks like it's completely cooked, but if you stick a toothpick through it, you pull it out, you may have some goo in there. So even though you may think that your bolt is completely heat treated appropriately, is the thermocouple within the right area in that furnace? Is it appropriately heat treated? This may require extra time to actually take a bolt out and actually do cross-section and look at the microstructure of your component to verify whether it's been actually heat treated appropriately. And even before that, once the component has come from the raw material, do you have the appropriate microstructure? Deleterious phases can also be not necessarily friendly subsea. And in the presence of hydrogen, you have the rapid fracture. Coating, are the appropriate coatings utilized? Some coatings may not be the best ideal coating for this service. And also, is the coating post-bake processes, are they appropriately done? Are they appropriately done immediately within that time duration as specified? Is that duration post-bake long enough? I won't get into the details about painting even also after coating. That's possibly more in the weeds for like task groups, but that's also another concern that was identified. Was those bolts appropriately painted all around? Is that the right paint? Is that the right coating, et cetera? Again, I guess I'm sounding like a broken record. Quality control and auditing. There really needs to be better oversight and really auditing further down the supply chain, further past the first one, the second, the third tier, and further down the supply chain. Are they appropriately following the OEM spec? Are they appropriately following the industry standard? And within that, is there checks and balances to keep up with the latest industry standard? Is everyone on board? Is everyone keeping up to date? And how long is that time period to implement the latest industry standard within the OEM spec? And then again, of those subcontracted vendors that are following the specification, is there compliance? And again, the management of change, that's also of concern. And finally, the fourth area is the operational procedures that is also a big concern. As Joe mentioned, you have this widget, but is the widget actually assembled correctly? And is everyone following the same installation procedures? Are these bolts assembled in the right pattern as specified per the OEM? Torquing. Is the guns that, sorry, forgive me, I can't help it. I've been around a lot of engineers and auto people, so I tend to speak kind of candidly. I apologize. But are the instruments that's used to install these bolts, are they appropriately calibrated to do the torque procedures? And cathodic protection, that's another area that really needs to be further explored. What is the appropriate applied current voltage system? Are the anodes replaced? Are they appropriately inspected when the stack is pulled? How much corrosion is identified on those anodes? And of course, you have the perfect storm, and I'd like to thank Trent for this, for reiterating this. You have your three circles: your environment, you have the load, and then you have the operation. Then finally highlighting on the operational procedures. The in-service inspection, how frequently are we inspecting? Is each inspecting being done on the same manner? How much detail are they being inspected? That's another concern. And what exactly is considered to be the appropriate data? Is some data just totally thrown out amiss? I would like to highlight Dr. McNutt with some of the previous failure that was identified for the Concorde. That little small debris from takeoff was the one small component that played part in that disastrous failure. It could be one small thing that can throw the whole three circles out of sync. And of course, we need to understand the G&G condition. Where is these components being used? What is the salinity of where the components are being used? And as Joe mentioned, some of these components are used globally and then brought back on the LCS. Is there a proper in-service inspection, maintenance does that salinity of what these components have seen in other charted waters, does that play a part? So highlighting a little bit more on design standards, I would like to note not all of the standards are listed that do have an impact. I understand, of course, some of these standards are different versus production versus drilling. And we definitely understand that there is task force and different groups that are addressing these concerns. You have your API standards, API 6A, 16A, 16F, 17A, and then recently API 20E, API 20F, API 6A 718, addressing bulk property requirements concerns, but there are significant material property gaps. They are being addressed, but what BSEE has identified out of the first evaluation is that there were different hardness, yield strength value requirement for fastener manufacturer. The other industry standards realize that NACE is a very in-depth corrosion standard, but they also do have different values and requirements. NACE MR0175, NORSOC M001, NORSOC M001 would like to emphasize that they also have different requirements for fasteners that are used with cathodic protection. There were concerns with, as mentioned earlier, ASTM B633 with following the latest edition of the standard 1998 versus 2007. 1998 had a different strength value of post-baking after 1100 MPa versus when the 2007 edition came out, they required post-baking after a hardness value of 31. There was also some different requirements, don't quote me, but there was different requirements in regards to the post-bake duration between 1998 to 2007. There was also different requirements for the pre-bake based on this, there were different requirements for ASTM F1137 and ASTM F1941 for the post-bake versus ASTM B633. ASTM B850 is your post-bake standard. Again, stressing there is a greater need for consistent harmonized requirements among industry standards for fasteners that are used on critical components used subsea. And again, stressing harmonization of the hardness, yield strength, ultimate tensile strength, the mechanical material properties, the coatings, and also the cathodic protection. Realize that these coatings that have been utilized were essentially zinc chromate and zinc phosphate, but this is something for the industry and possibly the research studies to look at, exploring alternative coatings like organic coatings. I won't throw out any names at this point, but I'm sure some of the tech experts understand where this is going. There is really a significant need, I can't emphasize this enough, for quality control of the fastener manufacturing processes and the material properties for critical subsea applications, these equipments that are being used. Some design factors, as I mentioned earlier, the three components that do play a part in the performance reliability: the environment, what these fasteners are incurred and experience under fatigue loading, and the raw material selection. These processes and procedures, what also need to be further looked at and what it has an impact is the casting of the raw material, the machining processes. Are the appropriate machining processes, are they calibrated, are they followed? And something to add is the rolled versus cut threads. The heat treatment processes, this goes from the beginning. If these fasteners aren't heat treated appropriately, then they have a different resultant material property values. And that goes back to the supply chain, making sure that these subcontracted vendors follow that spec and heat treat appropriately. And again, the coating processes. Is the appropriate coating used? As such, are they being pro-spec? And the cathodic protection also should be further examined. Again, just emphasizing, there are concerns with auditing only to the first-tier subcontracted vendor. There's concern with subcontracted vendor that are performing these different processes. Again, keeping up to date and following the use of older standards, and when are these standards being updated? What is that time duration, and what's the legacy for these latest standards being implemented into the OEM specs? Operational procedures. Fastener installation. This impacts the equipment reliability and performance. Is the equipment assembled appropriately? Is it being followed the required torque procedures? Is the pattern being performed in the installation consistently? Is the appropriate lubricant being utilized per the specification? As everyone knows, there's all types of lubricant that is being used. You have your moly coat, et cetera. But if in the interest of time, if there's another type of lubricant, that may also be a concern. And is the torque gun calibrated appropriately? Fastener inspection. Are the BOP fastener inspections done on a periodic basis? As Troy mentioned, there happened to be identified of a fastener failure issue when the BOP was brought to stack and on an in-between well maintenance inspection. Should we start inspecting a little bit more frequently? And if so, how many fasteners are being inspected when it's being brought to stack? Is it just one, or is it all of them? This should be considered. And are they also being replaced when that stack is brought to surface? Cathodic protection, that's something that still needs to be further explored and really fully evaluated. This can possibly contribute to the fastener corrosion and degradation if that system is not in sync and aligned. If that sacrificial anode is completely gone, you have the more promotion of the corrosion, degradation, acceleration. I won't get into the science of it and the kinetics and Fick's law of diffusion of the hydrogen ion diffusing into the substrate of the microstructure, and the difference between the BC structure and the FCC structure and how the hydrogen can get entrapped, and then we have a big crack. I won't get into that, but I'm sure the metallurgists understand the impact of that. And I'll turn it over to Doug.
Thanks, Candy. Let me summarize session one. We have identified, we believe, an industry-wide issue involving fasteners. It involves different components and different manufacturers. We have 9 different areas of concern or areas for improvement. That includes metallurgical properties, quality assurance processes for manufacturing, cathodic protection, inconsistent industry standards, coatings, installation procedures, inspection protocols, and design improvements. Furthermore, we're hampered by the lack of data sharing. I think the director mentioned we're aware of failures going back to 2003, but we don't know how many. As I mentioned, we have multiple parties involved, and there's legal and commercial issues that prevent data sharing, but that's definitely an area where we need to improve. The well control rule does provide for mandatory reporting, but that only applies to U.S. waters, and it would not cover failures that occur internationally. And in addition, I think the director mentioned this also, one manufacturer believes that this issue might impact onshore operations in pipelines. So there is a need for a comprehensive industry-wide data sharing program. Now with that, I'd like to make Joe, Troy, and Candy available for any questions. Go ahead, don't be shy. There's one back here.
Staff metallurgist at NIST, and I'm on the interagency panel. I was wondering if the incidence of these bolt failures and the use of higher strength bolts corresponds with going to deeper and deeper well sites. Has there been a change of materials used since, say, 2000 that I see Inconel being used, which is somewhat unusual, but has 4140 been the standard for a long time?
Again, it's too simple for me. I can do a fourth order nonlinear homogeneous equation, but the simple on-off switch. Typically, it's been 4140. However, for strength for certain components, like the blind shear ram, needed a stronger alloy. So in unique situations, there has been the Inconel 718, but typically it's been 4140.
Any additional questions? Okay, then, time for a break. Let's take a break. Remind everybody that there's water in the back. There's vending machines down one floor, and we'll take 10 minutes and come right back.
Let's just make it and come back right at 11. So we'll give people plenty of time to network. I know everybody loves to network. So we'll see you at 11, and I start on time.